In this video, we're following on from the last two videos where we looked at tension in a rope and also incline slope problems. So now let's have a look more at how we can combine those two concepts into some problems that involve pulleys. So let's start with the most basic pulley problem, which is you have two blocks, M1 and M2, connected by a rope with M2 hanging off the side of a ledge, a wall, a hill, mountain, whatever. So these two blocks are connected. And in theory, of course, all of these problems, what we're looking to do is first find the acceleration that this system is experiencing. And I say system because even though they're only connected by a piece of string, we consider, when we're looking for acceleration, how fast this whole system, meaning both of these blocks, are moving together. Because they're connected with a rope, however fast one moves is however fast the one that's being pulled is moving. So if you're looking for anything with more than one body, especially, you start with a free body diagram. So starting with M1, we have, of course, the normal force because it's sitting on the ground. We have the force due to gravity, which perfectly cancels the normal force. So net force in the vertical direction is 0. And it's being pulled, we assume, to the right by a force tension. Maybe it's not being pulled to the right. Maybe it's just sitting still. It's not moving anywhere. But either case, there's some tension in that rope connecting M2 and M1. For these kinds of questions, I'd like to typically define the positive direction as to the right or down. Whichever direction is down, I define as the positive direction. To me, this makes more sense because these systems typically tend to end up with the mass hanging off the ledge, pulling the whole lot down off the ledge. So typically that's the direction of movement, so I'd like to define that as the positive direction. So that's a free body diagram for M1. Let's draw M2. M2 only has two forces. There's the force of tension, holding the block up, and there's also the force due to gravity, which is just the weight of this block because it's floating. Great. And again, to remind you, I'll draw this in a different color. This is the positive direction, and in the case of M1, the right-hand direction is the positive direction because that's the direction it will move if M2 is going to pull it down. Is going to be falling. So, good. Now we've got these two. Let us now do F equals ma, or find the net force for each of these free body diagrams. So the net force on the left-hand side, like I said before, the vertical force is 0. So the net force in the vertical axis is 0. It's not moving up or down. It's sitting on the ground. So the only force that it feels is that tension force that's pulling it to the right. And F net, the formula for net force, is of course mass times acceleration. So we get the following equation. Let's just give it a number so we can refer to it later. Let's move on to the second one over here. Mass 2, the net force that it feels, again, positive direction is down. So is the difference between the two vertical forces that we see here. So let's try to end up with a positive number. So typically we'll go the positive direction minus the negative direction. So Fg minus the tension force is the net force. It's the difference between these two forces. So again, net force formula is mass times acceleration equals the force due to gravity minus t. The force due to gravity in this case is weight. So it is mass times gravity minus t. So this is our second equation now. So now we've got two equations. Let's substitute equation 1 into equation 2 in order to solve for A, which of course is acceleration. So let's find A. To do that, we substitute equation 1 into equation 2. So equation 2, m2a equals m2g minus t. From equation 1, we know t is equal to m1a So let's substitute that one in. Good. Now we rearrange to get A onto one side. M1A is equal to M2G minus M2A. We can factorize out the mass. Am I doing that correctly? No, I did that incorrect. My bad. We are moving the acceleration to the other side. That is correct. And that equals M2G. My mistake. I thought we had one acceleration. There are two accelerations, so we're going to factorize out the acceleration. So M2G equals factorize out the acceleration, and we're left with M2 plus M1. Great. So now we have this. We can rearrange again to leave A by itself on one side. We have M2G divided by everything in the brackets plus M1. So this is a really important result because now we see that the acceleration of this entire system is defined by whatever mass is hanging off, in this case M2. It's defined by only that mass. The acceleration of the whole system is based on whatever mass is hanging off. You'll see that this becomes important later in a future problem. So now let's put some numbers in here. Now we have a block of, let's say, 10 kilograms. Nice round number. And there's another block of 20 kilograms. And we'll call this again M2 and M1. So the question now that you might get asked is, 1, what is the acceleration? And 2, what is the tension? These are the two questions that you might get asked in a problem like this. So again, let us do a quick free body diagram. Free body diagram, we're going to disregard the normal forces for the 10 kilogram mass. It's only going to be the tension in the rightward direction. For the 20 kilogram mass, which I'll draw over here on this side of the screen, the 20 kilogram mass has downward force due to gravity, which is weight, and tension going up. Before we start any of the net force calculations, we want to find what acceleration is, which if we scroll up, we have this beautiful formula right here. M2 times force, gravity plus the sum of the two masses. So let's substitute in the values that we know. 20 will say that gravity is 10, and add 10 and 20 together makes 30, equals 200 over 30, and we get, what is this, 6.67 meters per second, 6.666 recurring. So we'll round up to 6.67 for now. Good. A good point to remember if you're not used to doing physics problems is, while you can round to 2 decimal points, when you do any further calculations, you should use the reoccurring number, 6.66666, so you don't get an error that carries all the way through your calculation. Good. So we've got that. Now let's do the net force for each of these free body diagrams. So for this block 1, the net force is MA. And we know what the mass is. We know what the acceleration is, 6.67. Again, when we actually put it in the calculator, it's going to be 6.66666. And we get 66.67 newtons. This is the net force that this block feels to the right-hand side. How do we know it's to the right-hand side? Because we defined this direction to be the positive direction. So because the net force that we got is a positive number, then it must be going to the right. So good. We also notice here that this block only has one force acting upon it, which is the tension force, which is convenient because that means the tension force is equal to the net force. And we just calculated what the net force is. So therefore, the tension equals 66.67 newtons. So we've already found what the tension force is. But we have a second free body diagram that we haven't tackled yet. So we should be able to get tension to equal 66.67 using the second block over here as well. Good. So the force due to gravity for this block is just the weight of this block, which is 20 times 10 equals 200 newtons. That's the weight. Good. The net force that this block experiences is m2 times acceleration. We know what the acceleration of this whole system is. We know how fast each of these blocks are actually moving. So it's 20 times 6.67. And if we evaluate that, that will give you 133.4 newtons positive, which means, again, it's going down 133.4 newtons because we defined this to be the positive direction. Good. So now we have another equation for the net force. How come we've got a weight 200 newtons, but the object is actually, the actual net force that this body is experiencing is only 133.4. So there must be a difference. And it just so happens that there is. We, again, look at Fg minus T. The difference in the vertical components is the net force that we're feeling. And this net force equals 133.4. Now we know what Fg is. We rearrange to find T, tension, which gives us negative, notice it's negative now, 66.6 newtons. Again, should be 66.6 reoccurring. And it's negative, which means the tension must be going in the upwards direction. We can remove the negative sign because we know that it's going in the up direction, which makes sense. Because if you were to draw this on a flat surface, block 1 and block 2, block 2 is getting pulled by gravity, so this is the force due to gravity. It's getting pulled back by tension. M1 is also getting pulled by tension. And the only other forces M1 feels is the normal force and force due to gravity, which cancel each other out. So we see that tension should be equal to each other, and the force due to gravity is the big one, which is dictating how fast this whole system is moving. Good. So now you've found the tension force in the rope connecting these two blocks, and you've also found the acceleration in that this system is moving. Both of these blocks are accelerating at 6.67 meters per second, which makes sense because it can't be free fall because there's another block that's resisting that movement. Good. So now let's move on to slightly more complicated question. Now we have two blocks and they're connected around a pulley. And again, let's use 10 and 20 kilograms for block M1 and M2. The question again is, what is the acceleration of the system and what is the tension in the rope? So the tension in the rope is acting upwards, and each block has the force due to gravity acting downwards. These are the only four forces acting in this system. Now for clarity, we're going to define this to be the positive direction, the right-hand clockwise direction to be positive. And just a tip, if you know what the masses are, the heavier direction is going to be the positive direction because that's the direction it's going to move. And that is intuitive for us. So what does that mean in terms of net force? It means that the difference in the two forces due to gravity, 1 and 2, is the net force. So let's have a look at that. Let's draw the free body diagram for both. And let us also look at what net force is. Here's the 10 kilogram block. There's tension pulling it up. And there's force due to gravity pulling it down. For the second block, same story. Tension, force due to gravity pulling it down. Let's write that in equation form. So the net force now for this whole system is the difference of the forces due to gravity. So Fg2 minus Fg1. This is the same thing that we did for the block hanging off of a cliff. So substitute in the values that we know, m2g minus m1g, that is the force due to gravity. Net force, again, is the system's mass multiplied by acceleration, mass times acceleration. But we're looking at the entire system now. So it's the sum of the masses multiplied by acceleration equals m2g minus m1g. We can factorize out the gravity. And now we can rearrange to find A for acceleration. Now, if you've been paying attention, you'll notice that this equation looks a little bit familiar. When we looked at the block hanging off of the side of the cliff, we saw that the equation for acceleration here is gm2 over the sum of the two masses. And I mentioned at the time that this shows that this acceleration only relies on the mass m2. And that this would be important later. If we look now, we see that the acceleration now relies on the difference between the two masses. So these are the same equation, except now the acceleration we see relies on a slightly different property. One is just the mass of m2, but now since they're both hanging, it relies on the difference between the masses, which makes intuitive sense because whichever is heavier is going to be the direction that this acceleration is going. Cool. So now let's substitute in the values that we know. G, let's say, is 10. M2 minus M1 is 20 minus 10. 20 plus 10 is 30. So we have 10 times 10 over 30, 100 over 30, which is 3.33 reoccurring. That's acceleration. Good. So now we have acceleration is 3.33. Let's go back to our two force diagrams, free body diagrams, and go for the net force that each body is experiencing. So the net force that this body is experiencing is the difference between the vertical forces. So remember, we defined the clockwise direction to be positive, which means that this is the positive direction, and in this second free body diagram, the down direction is the positive direction. So now let's use the positive minus the negative, substitute in what we know. And now let us also find what F equals ma is for this, because that is what the formula for the net forces. So m, which is 10, multiplied by 3.33, of course gives 33.3 equals T minus, what is the weight of this object? It's 10 times gravity, which we'll say is 10, is 100 newtons. Rearrange, and so for T, 100 plus 33 gives you 133.3 newtons of tension in the positive direction, which of course is upwards. For the right-hand side now, net force, again, is the positive minus the negative direction. And we substitute in all the values that we know, m2 acceleration, m2 g minus tension, m2a is 20 multiplied by 3.33, which is 66.6, reoccurring. m2g is just the weight, so it's 20 times 10 is 200 newtons, minus t. T equals 66 minus 200, which of course equals minus 133.3 newtons. And because it's minus, it must be going in the opposite direction, so this is 133.3 newtons in the upward direction, which of course matches, which is your sanity check. They have to match, the two tensions have to match. So now you've found the acceleration for the system where they're hanging connected by one rope over one pulley. You found the acceleration. You've noticed that the acceleration now is the variable is now dependent on the difference between the two masses. And then again, we've had a look at the free body diagram. We've carefully defined which direction is positive, in this case, the clockwise direction, and we've done the net force equation for each of the free body diagrams. So moving on, let's now look at what happens if we combine this with an inclined slope equation. What if now we have a block on an inclined slope? Again, let's say it's 10 kilograms. But this time it is connected to another block that's hanging off the back end. Again, let's say 20 kilograms, just for simplicity. Block M1, M2. Now you have this system. Let's say that the slope is 30 degrees from the horizontal. And let us now look at the two forces that are now happening. We have the force due to gravity for this guy, which is just weight. So it's 20 times 10 equals 200 newtons. We have the force due to gravity from this guy. If you remember, the force due to gravity for a block on an inclined slope is mg sine theta. This is from the previous video about inclined slope, which you'll see in the little card that will pop up on your screen now. I recommend you to watch that before continuing with this video. So now let's find what the net force of the system is. Of course, every time you want to find acceleration, we start with the net force equation. Net force is the difference between the two forces that we are looking at. Let us again define this direction as the positive direction. So we take the positive minus the negative. So that is our net force equation. Let's substitute in what we know. The net force is mass times acceleration. Again, it's the sum of the entire system's mass times acceleration. And then this is m2g minus, and then again, careful, if g1 is mg sine theta. Rearrange to find a. So we have m2g minus m1g sine theta over the sum of the two masses. Good. If we were to factorize out the g, you'll see again that the acceleration, let me just factorize that out really quickly, m2 minus m1 sine theta over m1 plus m2. You'll see again that the acceleration is only dependent on the difference between the two masses and also the angle theta, which makes sense. So you'll see that these are all variations on the same equation, except now we're looking at the difference between the two masses, and now we have an added angle component. Let's factorize in all the values that we know. We know that m2 is 20 times 10 for gravity. m1 is 10 times gravity, multiplied by sine of theta, which is 30, plus the sum, which is 10 plus 20. Simplify all of that, you get 200 minus 50, because sine theta equals a half. Another identity you should remember. And this, of course, equals 5 meters per second. So this is your acceleration right here. Good. Now we have acceleration. We want to find what the tension force is that each of these blocks is experiencing along the rope. And to do that, we will draw, again, free body diagrams. So free body diagram for the block on the left, which is the one on the slope. So this is block M1, 10 kilograms. And we'll just draw horizontally, but there's a tension force pulling it to the right, and there is the force due to gravity pulling it down the slope. And then for the 20 kilogram block, there is tension pulling it up, keeping it up, and the force due to gravity, which is just weight, which is just 200 newtons, pulling it down. Again, we have defined this to be the positive direction, and we've defined this to be the positive direction because it's up the hill. So, net force equations for each free body diagram is tension, which is the positive direction, minus the negative direction, minus Fg1. Net force equation, mass times acceleration, tension stays the same. Force due to gravity, again, it's on a slope, so it's mg sine of theta. Substitute in all the numbers that we know. So this is 10 kilograms multiplied by our acceleration, which is 5. T minus mg, which is 10 times 10, multiplied by sine of theta, which is 30 degrees. And rearrange the so for t, and we have 50 plus 100 sine of 30, which is a half. So this becomes, this is 0.5. It's an identity you should remember. It's 50 plus 50 is a 100 newtons in the positive direction. So now let's move on to our second free body diagram. We should also get 100 newtons, but in the negative direction now. So net force equation equals our positive direction minus our negative direction, which is tension. Net force is mass times acceleration. Mass times acceleration here is 20 kilograms multiplied by the acceleration, which is 5. 200 newtons minus t. Rearrange to find t, and we'll get 100 minus 200, which of course is negative 100 newtons, which makes sense because it's 100 newtons going in the negative direction. So now you've found tension for a block that is sitting on a slope. Now there are two variations of this. Let's have a look at what happens if now we swap the masses. Now instead of the 10 kilogram block on the slope, we have the 20 kilogram block on the slope. And the 10 kilogram block is hanging. We've got 10 on the slope here, and on this one we've got 20 on the slope instead. So we've swapped the two masses around. The force diagram is exactly the same, force due to gravity, tension, tension, force due to gravity, and of course block 1, and block 2. Good. So very quickly, let us find what the net force is. The net force for this entire thing is just the two forces minus each other, right? Positive direction minus the negative direction. Again, this is the positive direction. That's what net force is. Let us quickly substitute in everything that we know here. So we know m2g minus mg sine theta, which is the force due to gravity on an inclined slope. And net force, which right now we'll just leave it as F net. you'll see why in a second. So what's mg sine theta? That's Fg1. What is mg sine theta? Let's find that out. Mg sine theta is 20 kilograms multiplied by 10, and sine of, this should be 30 degrees, sine of 30 degrees. So this is 200 times 0.5 equals 100 newtons. Good. What's Fg2? Fg2 is just the weight, mass times gravity, equals 10 times 10, 100 newtons. Well, that's interesting. They're the same. So what does our net force equation become? Fg2 minus Fg1 equals 100 minus 100, which is a big 0. So our net force here is 0, which means that these blocks are not moving one way or the other. They are in equilibrium. So you might also get this result. Keep in mind that this is a possibility. So now the question is, at what angle would this system tip to the left or to the right? And for this question, it was easy because we know what the angle is that equilibrium is at. But for a problem where you don't know what that angle is, what would that angle be? So now let's just swap up the masses. Let's say it's 20 kilograms and 30 kilograms so that they have no relation to our previous numbers. Force diagrams are the same. And Fg2, we are ignoring the tension right now because we're not looking for the tension. Again, this is the positive direction, so our net force is the positive direction minus the negative direction. Now, let's find where the equilibrium point is so that we can find what that angle is for this system to not be moving at all. So for equilibrium, we want the net force to be equal to 0. Therefore, how do we make this side equal 0? Fg2 equals Fg1 will give you net force equals 0. So in this case, if these two figures are equal, let us substitute in the equations. Fg2 is just the weight of block M2. Fg1 is force due to gravity on an inclined slope. Mg sine theta. Good. Rearrange to find sine of theta, which is M2g over M1g. The two g's cancel. So we're left with sine theta equals mass 2 over mass 1. And to find theta, of course, we just take the inverse or arc sine. And good. Now we know what M2 and M1 is. M2 we said here is 20 kilograms and M1 is 30. So we have the sine to the negative 1 of 20 over 30. And if you put this into your calculator, you will get 41.8 degrees. So with theta, the angle of that slope at 41.8 degrees, neither block is moving. Your net force is 0. But if this were to increase, if you were to go to 42 degrees, then your blocks would move in the negative direction. They would move down the slope. So if this were to increase, then it would make sense that this block would move down here. And if they were to decrease, then they will move in the positive direction. If they would decrease, then it will move down this way. So now you found the equilibrium point. A higher angle will cause the block to move down the slope, and a lower angle will cause the block to move off the ledge. So that is the third variation of the inclined slope with a pulley. And of course, if you wanted to find the tension, you could go about finding the tension in the same way by drawing your two force free body diagrams. Good.